So in this video I'll discuss maximum likelihood estimation in R. Okay, now there are two ways in which we can do this. So we'll say two ways or two methods. Okay, so first of all, we can do so the first part, A, will be through inbuilt functions in packages Okay, now how do you do so? Well, example could be the fit dist R in the mass package. Okay, so for example, you go there, you do fit dist R. So what does it say? It says what? Fit dist R, maximum likelihood fitting of what? Univariate distributions. Okay, so this is how it looks like. Okay, so fit.dist R, if I want to fit any data, and the distributions that I can fit are this. So these are, it's a box one, like you've been boxed into what? Distributions that can be recognized by the function. If you have any distribution outside of this function, it means this function is then useless or needless. It won't help you in any way. So for example, I can use this to fit, let's say, a normal distribution. Okay, I can use it to fit a Poisson distribution. I can use it to log normal, logistics, t, chi-squared, and so forth. So I'll do some few examples. Okay, so I'll assume that I have a data 1. Okay, and this data 1 is that I simulate observations from the from the Poisson distribution. To do so, I will have to do rPois. So that's the random number generation from a Poisson distribution. So Poisson is in the start package, and rPoisson is what? Is generation. If you go here, it tells you that random number generations. Okay, density distribution function. This is random generation. So the random generation is a R. Okay, so I do this. Okay, my n is maybe 40, and then my lambda is equal to, let's say, 5. Okay, so I simulate this observation because this is this data. I can plot a histogram of it just to see how it looks like. Okay, and we get something like that. Of course, I can do the margins of the plot to let me see it quite better. Okay, so I'll rerun this and see. There it is. So this is my frequency for this data, right? Okay, now I want to fit a Poisson distribution to this data. So I call for ML estimation using ML estimation. Let me just say ML estimation because we still know this. Okay, now so the density x is the data, right? Okay, so s, the density function is Poisson. Remember the way Poisson is spelled over there. If you are in doubt, you go there and look for it. Okay, so there is a big P. So if you don't do it like that, you won't be able to get a better get results for it. Okay, so the density function Poisson. Start values, we may ignore it, but I mean, if it can be provided, and if you go here it will tell you what the start value name list. So if you want to do it, you need a list of it, okay? And if you want, you can go to the details and look at how the start should be. Okay, so look at this. So our lambda is 4 point something. Remember, our lambda is 5, but we got what? 4. There's a standard error. So this is how you use inbuilt functions to do this. We can check for weak loss of large numbers. So I check by increasing the sample size. I go through the same scenario, and now you see it's now getting closer to the 5. If I increase this to, let's say, 4,000, okay, I can go through the process. You realize that the 4.955, so it get closer, quite closer to 5, and that's it. Okay, so let me revert to the 40 and so forth. Now, one other way is to also to use another function using mass package. So we use function from mass package. This one we can also fit it using the fit.dist.r package, fit.dist.r plus package. Okay, so that there we need fit.dist.r fit. So fit dist, there it is. So this fit dist. Okay, so what does it say? It says that univariate what distributions to non-censored data. So it can do, you can use it for censored data, univariate to distributions, univariate distribution to non-censored data actually. So what is censored data? The censored data is when you don't have all the you don't observe everything so let's say if it is a lifetime, you are following people who are infected with a particular disease within a certain number of years, let's say 3 years, and then after 3 years somebody has not died. It means the person has been censored. It means to get the person's survival time, you have to follow it more, but the experiment has ended. So what do? You say it's censored, but we can still use statistical methods to project into the future what is likely to happen to such a person. Okay, so there you have this. Okay, so here we can also use that one. You remember this one is Poisson, right? If discrete is true, we can use the Poisson distribution. So how is this function used? Of course, we can copy this. It's easier to copy, okay, and paste, and then you fill in what you need. Okay, so here I'll need the data. So what is my data? My data is data 1. Okay, all right, and then the dist R should be Poisson. You notice that here the Poisson is just what? Is just POS like this. So method by default it uses maximum likelihood. Okay, but if I like, I can just delete the rest so that I don't have any influence. Next is a start value. We can leave it at null or provide it if you want to do so. Okay, remember that discrete, we can say discrete is true because it's a discrete distribution, right? Keep the rest, we can let it be what the default value. Okay, so let's see. Okay, so we do this. The estimate for this is what? 5.1. Remember the parameter is 5. Now why is it that we have differences between the ML estimation, the mass package, and so forth? If we go to the mass package, I can go back to show you. By default, you see, by default, it uses a procedure. Remember in your mathematics course, numerical analysis, or when you want to find simply when you want to find the values of zeros of a function, there are so many methods you can use. Okay, Newton-Raphson's and so forth. When it comes to that's what we call optimization. Now, so there are so many methods that you can use to do this optimization. Okay. Now, in this case, let me go back and check. Yeah, so I'll explain it when we do our own. Yeah, so you see, when we call these functions, it rather calls this perform the distribution actually by optimization. So it calls a function like this, which I will use later on for us to be able to do our own maximum likelihood. In other words, when we state our likelihood, we should be able to do that. So that's the general purpose optimization. Now, what I'm saying is that the method by default usually nail the mid. Okay, but there are others that you can look out for. Okay, so the method here, you see, there are the mid, BFG, CG, simulated, annealing, and so forth. Okay, so if once those two uses different methods, we are bound to get what different values. Which one is good? Well, it's relative, and also it depends on the circumstances that you have. Yeah, the circumstances of the data. But some methods, if you look at the numerical analysis, some methods perform better than the others. Sometimes under what different conditions, and so forth. But we are not so much into this, so I'll leave it at this. But I will still talk about it when we get to our own likelihood. So one, we can use this. There are several others packages that you can check for. Like I think ML4 and etc. There are so many of them you can check online. There are nonlinear methods and so forth that you can also check for. So now I go to the B part, which is using user defined. So this one is user defined. I am terming it as a user defined ML, maximum likelihood estimation. And what do I mean by user defined ML? Well, you see here, the previous two that I have done, I have not really done any. I just call the data, and then I get some functions in R. I just call them, and they fit my distribution for me. Okay. So anything, if I only did Poisson, let me, because I will talk about normal distribution, let me do normal distribution as well. So let's say I come here, I want the normal distribution, I want a data set, and even my data, the one that I talked about, I can check if I can fit normal distribution to it. Okay, so let me see. Okay, so when I fit this normal distribution, it says it has a mean of what? So the data, I can actually fit a normal with mean 5, 1, 2, and then standard deviation this to it, even though it is what? It's discrete. Okay. So essentially, if I want to, I can superimpose the density function. You see my plot, the plot of this, or this one is a whatever. I don't. Let me check the sample size now. No. Okay, no, I mean the data. So I should know how long is the data. So the data is okay, data 1 is 40. Okay, so I don't know if I use the 40 because remember I changed the formula. Okay, but essentially for this data 1, this is the mean, and remember the for Poisson distribution, the expected value is lambda. So you see it's not far from it, and the variance, but remember for Poisson the variance is lambda as well. But look over here, the variance it's also around, let's say, because we have to square that 2.9, so it closely relates to what you find. Okay, but those who are interested can look at for what we call over dispersion in data sets. Okay, zero inflated and over dispersion. That's when, theoretically Poisson distribution, the mean and the variance should be the same, but in reality, in practice, the mean and variance may not necessarily be equal to. Okay, so over dispersion, and sometimes you have zero inflated, you have so many zeros or counts of zeros and so forth. So it's one of the active areas of research in statistics, and those who are interested can look out for. So for example, in our department, Dr. Idi does so much research in that field. That's his area of specialization. Okay, all right. Okay, so now that's it. So we can fit a normal distribution also to a data set. If I do that, I can essentially I can name it. Okay, and if you name it, you can check either summary. If summary works for this, you see it may not work, but if it doesn't work, we still have a way of getting all the things that we get from this. So summary tells us that this, if I fit that model, I have the estimate, I have the standard, or I have the variance covariance matrix. Okay, I have n, and then the n log likelihood. Log likelihood. Why is the log likelihood good? Okay, so sometimes you need all this information, because remember that when you fit models, you may want to compare which one fits better. To do so, you need what we call the archaic information criteria and the Bayesian information criteria. So AIC and BIC. If you Google check this, you will find so much on it. So the AIC, for example, relates what relays the log likelihood. So it's like 2 times the log likelihood, and then also you add it to your the number of parameters. That is 2 times the number of parameters, and so forth. So you need it. So the archaic information criteria, okay, will be 2k times minus 2 times. So if I want to write a function to calculate the information criteria to, it's just 2 times the number of parameters that I want to estimate minus 2 times the log likelihood. So it's essentially, if it's a function, I can call it like a function. Okay, so this function will take in k, which is the number of parameters, and then L, which is my log likelihood. Okay, or let me just log likelihood value. Okay, and k is the number of parameters. So it is essentially 2 times the k, which is the number of parameters, minus 2, okay, times, and then I have log of the likelihood. Okay, so if I have the log likelihood already, then it's just the log likelihood. Okay, like that. So this will give me my archaic information system, and as archaic information criteria, I should say, not criteria, and so forth. Okay, if we want to talk about BIC, we can also find it. So it's the archaic information criteria. Okay, so later on, when we are fitting models, we may use this to test which this thing fits the data better. Okay, but for now, let's just move it. But I just wanted you to know that when you do maximum likelihood, you have most other estimates that you like the variance covariance matrix and so forth. In in the Optim, when we move forward, we are going to get a Haitian matrix. When we get a Haitian, we can also use that to get our standard error. Okay, here it's easy to get it from our variance covariance matrix. So if I recall my variance covariance matrix, I should be in a position to get my standard error of each of them. Okay, so the variance covariance, because we have two parameters, which will be this. So this is the variance and then the covariance. Okay, so the variances are on the diagonal, covariances are on the up diagonal. Okay, so let's move on. So that's how you estimate or do maximum likelihood estimation with inbuilt functions like that. Okay, now we move on to user defined, where we have to write our log likelihood and then optimize it. Okay, now here what you need to do is that I'm going to provide with a syntactic structure. So here, estimating log likelihood, okay, functions entails two step process. So first we declare the log likelihood function, which is done in general terms. Okay, then we optimize the log likelihood function, which is done in terms of a particular data set. So I state my function, and then the data set that I'm interested in fitting the model is I optimize my function on it. So the values of the or the values that will give me the highest, okay, probability of obtaining that sample is what I will use as my maximum likelihood estimate. So that is as simple as that. Okay, now so the log likelihood function and the optimization command may be typed interactively into R, and that's what we are going to do now. Okay, so there are two, I said it's a two-step process. Okay, so what are these processes? Okay, first, okay, we say we would declare the log likelihood. So declare, the first one is declaring the log likelihood function. So that's the first one. Now how do we do this? I'm going to give you a general form of how we can declare our log likelihood. So basically, the log likelihood function is declared as an R function. So you write an R function for it. So we'll go back to our results, or let's say our class on function. So we use that technique in this. Okay, so first, so what are the function in R? So functions take this function, or the log likelihood function that you write in R, take at least two arguments. Okay, first, the function require a vector of parameters. Okay, second is it requires at least one data object. Okay, note that other arguments can be added to this if they are necessary, but if not, the two are okay. So you have your parameters and then the data. One may ask, we are now trying to estimate parameters. Why is R asking us to input in a parameter? That parameter that you put in is used as a starting point for the optimization. So the way we do our theoretical maximum likelihood, in practice, although it's similar, it's not exactly the same. Okay, so in a course like 333, when we ask you to find maximum likelihood, you go through the theoretical process and then you say, okay, for example, the Poisson is the mean. The maximum likelihood estimate of the parameter is the mean. So given a data set, you find the mean. and then you say this is a maximum likelihood estimate. In practice, that does not work that way. Okay. Remember that we want the for a particular data set, we want the values of the parameter, okay, or estimates that will give us the highest probability. So what we do is that, given the data, we give the routine a starting value, then it will iterate. At every iteration it gets a new value for the likelihood function and so forth. So you do this, and then you check how close is it to the unknown parameter. Okay, so you do this over and over and over and over again until you get to an appreciable level, and then you say this is the estimate. Sometimes you don't get the desired level, however the routine cuts off, or it stops, and then report on the value that is the last one, and that is taken as a maximum likelihood estimate. So that's how this is done. So to do this, we will need a likelihood function. Then we now optimize this function in relation to the data set at hand. So how do we do this? So the first, we need a function. So I'm just going to give you a generic function that you can follow for this. So this, you need the parameters, which is a vector, okay, and then a data like that. Okay, remember that is at least what you need. You can add more if you want. And why are we doing this? We are doing this in the sense that it is not every time that you will have the distribution in an R package. So let me tell you one of my students at the MPhil level, I will make the paper available to you, did some work in which we looked at the generalized Pareto distribution. So the generalized Pareto distribution covers a wide range of distributions that may have heavy tail, it may have lighter tail, or it may have a right endpoint. Okay. Now, so these distributions, this family of distribution helps in fitting, for example, tails of distributions. So maybe I have claims data for an insurance company. I know that the insurance company will be so much interested in large claims, because when those claims happen, it can bring solvency or liquidity issues. Okay, so you want to see how large your claim can be. So in doing this, we can fit a generalized Pareto distribution to it. How do we do so? We will draw a line we call the threshold, so that any claim that is over that threshold, we take it into account in fitting this distribution. This distribution has very wide properties. Okay. Now, but when you have a data set, because this is a continuous distribution, so when you have a data set that is discrete, okay, so for example the Poisson one, we are recording the number of times events happen in a particular time interval. Now, because the generalized Pareto distribution is a versatile distribution, we may want to fit it to it. But we are constrained with this discrete case. So what we'll do is that we can discretize this Pareto distribution to get a discretized version. So that discretized version can be of what? A Poisson distribution. Okay. So then we can fit it quite easily. Okay. Now when we do that and we have fitting our distribution and we want maximum likelihood, you won't get it in any R package. So then you have to write your own function. That is where some of these things comes in handy. Okay, because distributions are not exhaustive day in, day out. There are more distributions that are coming up. When it comes up, you must estimate it. If you are using maximum likelihood estimation, then you need a likelihood function. You need to optimize it. So that's where this class is of much importance, or this part is of much importance. Okay. So once we have this, first of all, we do some declarations. So the declarations will be like, maybe we find the sample size, because we need a sample size in the log likelihood, and so forth. Okay. And then we find our log likelihood. So this will be the log likelihood function. It's nothing else like the log likelihood function. Okay. And then what next? We return the negative log L. I'll explain this. Now, sorry, it's log L. Log L. Okay. So in now, remember that I said this part of the estimation, the user defines two parts. First of all, we formulate our null hypothesis, or the declare it, and then we can optimize it with respect to the data at hand. So in the optimization routines in now, they all find minimum values. Okay? So, but we are interested in maximum. So what do we do? The workaround for this is that so the workaround for this is that you negate your log likelihood, then you minimize it. So when you minimize it, it's equivalent to what? Maximizing the log likelihood. So that's the approach. That's why we have log. So you make sure that all your functions that you write should return on the negative log likelihood. Okay. So that's it. So that's the first part. Okay. What is an example? Let's go and look at the Poisson distribution. Okay. So now the Poisson distribution, let's start with the Poisson. Okay, let me just pause and do my. So now I have my whiteboard. Let's see. Okay. So we say Poisson distribution. So let's first start with the Poisson. So Poisson distribution. Okay. All right. Now, so what is the probability mass function of the Poisson distribution? From our elementary statistics, if x is a random variable, then we know that lambda is our rate function. Then the Poisson distribution is of this form, right? So what is here? And it goes up to what? Up to infinity. Okay. Now, then from estimation theory, we know that the log likelihood, okay, the log likelihood as a function of this on the vector data, okay, is equal to the product okay, so it's equal to the product I moving from 1 to n, okay, p of x is equal to xi. Now one may ask why n? Because for a data we must have our data to have a size of size n. In other words, it must have what? A sample size. Okay, we cannot have the data and the data too is what? Infinite. Okay, so essentially if we do this and get our log likelihood of gamma, okay, lambda, okay, will then be equal to because when we find the log, this becomes sum, right? Okay, so essentially you get sigma xi, right? Okay, then len with lambda, okay, minus n lambda, okay, minus sigma len y, sorry, x, x factorial, right? Actually xi factorial, because each of these should have I, so xi factorial, so then xi factorial, like that, okay, factorial, okay. Now, so if you look at this, remember that in your estimation class, the theoretical classes, what you'll be interested in is that once you have this, your log likelihood, you find what? The partial differential of the L with respect to what? In this case, gamma. And then you set it to 0, you find the value of lambda will give you some x bar, something like that, okay, in this case. But here, so it means that when you are doing this, any value or any of these expressions that do not include lambda, the differential will be 0. So in other words, we can just ignore this part, right? Because that part does not include what? It does not include lambda. So delta L over delta lambda will be 0. So essentially, what we need is just L lambda x, okay, or it's a vector. So xi, of course, this will be I. If I put I must put I there. Okay. Then len lambda or log lambda minus what? N lambda. So this is our function, or that our log likelihood function. So this is what we are going to program in R. So we go back to R with this idea, and then we do it. Okay. So for Poisson distribution, so our function will be maybe log like dot Poisson. Okay, so this is a function. Remember, we said it should take path and what? In this case, the parameter will be lambda and data, right? Okay, so there we now. So what are the declarations? Well, we need n, right? Remember, in the formula we have what? N lambda. So we need n, right? Xi's are the data points. Okay, so n is equal to length of, but I'm using length because I assume that data is in a vector form. If it is a matrix, then you have to either use n row or n columns, depending on how your data is arranged. Okay, so now log L will be equal to what? When you come here, you have what? Sigma xi. So that will be sum of what? Xi, and in this case it's sum of data, because my sum of data, okay, then I multiply sum of data by what? The log of what? Lambda, the log of path. Okay, if I like, I can just change this path to lambda to make it easier. Okay, so two ways. I can put lambda here, or I can also say lambda is equal to path 1. Okay, so maybe let me just put lambda to make things easier. Okay, so that's the first part, and then minus, okay, n times what? Lambda. That one is not log. Okay, so that completes our likelihood, log likelihood function. Okay, then what should we return? Remember, we return the negative of the likelihood, right? So negative log L is what we will return. Okay, so that's the first part of the way. Now that we know this, let me comment these ones out because they are actually not eligible. If we run, we'll get results because it doesn't have some of the data. Okay, so that's it. So what about the second part? So the second part will be about the optimizing the likelihood. So the second part, the B, what did I use at the top? I said declaring the likelihood, so I. So this will be I. No, I. It's in caps. I. So I will be optimizing the likelihood, the log likelihood. Okay, log likelihood. Now, how will this be done? Well, to do this, we have to call for the function, an optimization function. And the easiest and the widely used one is optim. Okay, so optim, remember even the function we use in the inbuilt functions that are used for uses optim. So optim is like this. So optim needs parameter, which is the starting point of the parameter for the iterations to begin. A function, which is the log likelihood function. GR is a gradient function. If you have the function, you remember that in numerical analysis you have gradient descent and so forth. Okay, you can speed up your iteration if you provide out with the gradient function, so that it doesn't have to differentiate it to get it. Okay, so that's it. Then more importantly, so this one we can always use it. More importantly is the method, right? So the method, as I was saying, there are so many methods. Each of them has its advantages and disadvantages. Okay, so now we now have a method that we'll use. So maybe we should first use the first one. If you want other ones, you change it. The other ones are BFG, CG, and simulated aligning, which is SUN, and so forth. Yeah. If you need it, you just bring it back. Lower and upper are for the parameters. So if you have a parameter, you have to indicate to R what is the lower bound, what is the upper bound. Okay, sometimes you just have to provide it with some large value that you think this the estimate will not reach there, so that it searches within this. Remember, everything we are doing is iteration. If you provide a starting point that is closer to the solution, it will reach there faster. So if my solution, for example, my lambda is 5, because this simulation, so I know what I want, and then I go and start from 1,000, and somebody starts from 2, the person will get to 5 faster than the one who is coming at from 1,000. So that's the idea. Okay. So you provide it with. So for example, in this example that we are talking about, for Poisson distribution, the parameter lambda is greater than 0, right? Okay, so it's a rate. So we will say we will give it a lower bound of 0 and then an upper bound of either infinite or some very large value. Okay, control, we can control list to control our parameters. Hessian, you remember in likelihood we can find the standard error through the Hessian matrix. Okay, so when you do your likelihood like that, you can get a Hessian matrix from it and so forth. So yeah. So you can get your Hessian matrix. Okay. So now what next? Before we'll be able to do this, okay, we need a data that we can use to do that. So our optimization routine is like this. So now I'm going to take a practical data set and walk through this. Okay. So before I'll be able to do that, I need a data set. So data, remember we already have data, right? Data 1. So then I can continue with my optimization. So my parameters, I can say, let me start from 1, right? Then the function that I want to optimize is a log-like Poisson, right? This one I must put it in quotation marks so that it is applicable in the global environment, and then I run it again. So the function that I want to optimize is this one. Okay, the method I have said near the mid, I have provided this as 0, this as infinity. Control, it can be Hessian matrix may be true. So let's see. Okay. So it tells us that error in agreement data. Okay, so look at what is happening. So each of these you learn from it. So I commit errors and then we see. Remember, so we are calling the likelihood Poisson. If I go to that function, it needs 2 arguments, lambda and data. So here, the power is assumed to be the lambda, but the data is not there. So what I need to do is to provide it with data. And that's the more reason why, if you have this, you can provide your own arguments. Okay, so data, and it must be the same as what I have in the function, is equal to data 1, right? Data 1. Okay. So still I have an error. It says error in could not find return. Return. R-O, let me. You see? So it means I made a mistake up there. See this? Instead of return, I wrote this. So you see, now it's blue. At first it was, but it did not occur to me. So, I mean, the importance of this is that as we go through this, it helps you to also learn the case when you have problems, and then you can resolve them quite easily. So I go there, I change, I rerun, then I come back to my data. Okay. So now there's no error, but there's a warning. Okay. So my parameters has been estimated. Okay. I got the parameter estimate to be 5.12. The value of the the likelihood function, negative 129. Remember our AIC. So we pass this value through that to get it. When I finish, I will do this and then find the AIC, because the AIC is also a function in R. Okay, so function gradient convergence is 0, and then yeah, so that's it. Okay, so that's how this is that. But the warning is important. It says that obtain now the mid lower bound can only be used with method LFGS. So it means the lower bound that I provided for L, it doesn't need it. Okay, but if I was using this method, I need it. So let me put in that method and see what I get as my estimate. Okay, so this one too, it gave me 512. Okay, it gave me a value, the count, convergence, and so forth. So that's in a nutshell how you do your maximum likelihood on your own. Okay, so what else do we do now? So that's the first example where we have done our own this thing too. So I said I'm going to do the fit dot p is our Poisson. So if I run this, you see now if I display, then it will give me all the results. Okay, like that. Okay, so okay, so now what I'm going to do is to do another example using the normal distribution. Okay, so let's see. Okay, so let's see, second example, normal distribution. Okay, remember, if I have any data and I want to fit a normal distribution to it, I can. Okay, so let's look at the air quality data. Air quality. So the air quality data, okay, it talks about the air quality or zones, so and so. So there are some, it's a data frame of 153 variables and so forth. Okay, so I want to see some characteristics of this data. So let's say I want to see histogram of air quality data. And I need, let's say, the wind, which is wind speed. So let me see how this yeah. So this looks like a normal distribution. So my preoccupation is to fit a normal distribution to it. Remember, I can do this using what? The inbuilt functions. So let me see with the first one, fit dist r. Remember, we've done this up here, so I can go there and copy and paste some of it in there. So fit dist r. Okay, so first of all I do this. So my data is this, rather, right? I change this. Okay, now what I don't know is how this one, so the density should be so stated. So I go into the help files for fit.dist. Yeah, so the density from, so normal is just normal. Yeah, it's just normal. So instead of Poisson, I'll put normal there, right? Okay. Then I fit this. Okay. So I fit it. So fit N1. I fit it. Okay. Okay, so this is what I was talking about, the AIC. So AIC is actually a function, okay, and you can look at it. It takes it from the object list, of course. K. Okay, so when I have a function like this, I can compute the AIC. 322. Now I can also do this fit using the other one, which is fit.dist in the mass package. Sorry, fit this R in the fit this R plus package. Okay, so here data will be air quality. Distribution is no more Poisson. I have to go and check whether that also recognizes normal distribution. So this is the R in the let me just do this. So it is not every time that you may, if you have it up and fair enough, but if you don't, you can always refer to it. So I just want to see how normal distribution is stated in this. Okay, so let me try and say normal and see whether it will work. Discrete is false because this is not a discrete distribution. The normal function must be satisfied. So normal, let me see. Okay, so you see it's norm. Okay, so the naming is very important. Fitting the distribution norm by what? Maximum likelihood. Parameters, estimates, and then the standard error. The standard deviation is this, and the standard error. So that's how this is. But now, what we are left with is that we have to now do our own in our own one. Okay. So our own will be that we need a log likelihood and then we'll optimize it, right? Okay, remember that you can put the log likelihood and the optimization in one function so that you just take your data and then you pass it through and then you do it. So that will be like the fit this R that we have done. Okay, but for now we'll do it separately. So norm, so I'll name my norm dot likelihood will be what? Will be a function which will take in arguments and pass and data, right? Pass and data. And let me say is y. So y is the data. Okay. Then what is this? First of all, I will look at my length, the length of y, which is the data. So length y. Okay. Then I need mu and sigma, right? So my mu, because this one the parameters are 2, so I will have to pass in. So they select the first one as mu, and then sigma. Okay, here you have to be careful. You know, if you what is your standard deviation? What is your so I'm taking it as variance, right? So variance. Okay. Then the log likelihood. In this case, I can write it for the normal case, let me go up. Okay, so normal distribution so for the normal distribution, your log likelihood, I'm just writing the log likelihood. Of course, you can take any book or go back to your notes and notice how that is. Essentially, you remember your distribution is this 1 over sigma 2 pi. Then you have E half, okay, x minus mu sigma all squared, right? Of course, sigma is greater than 0, mu it belongs to what? R, something like that. Okay. Now, so you formulate your likelihood. Your likelihood function will be a function of mu and what? Sigma on some x bar. That is just the summation I moving from 1 to n, f of xi, right? So if you put this in, you can find your likelihood. Okay. Xi. Okay. So like that. Okay. Now, essentially, if we put this one in, and then we find our we find the logs of it, we are going to get L mu sigma. Okay. Sigma squared. Okay, so this is squared as what? Okay, as. Okay, so now it's so negative half okay n log 2 pi, okay, minus half n log sigma squared minus half, so 1 over 2 sigma squared, okay, and then times, so this is times sigma xi minus mu all squared, something like that. Okay, so that's our log likelihood. So this is what we are going to program in R. So we'll have maybe 0.5 times n log 2 times pi, because pi in R is pi here. Then minus that n times log sigma squared minus this, and then we sum the difference, right, between it. So that's how we're going to do it in R. So our log like should be the same as negative half. It's easier to write a 0.5 because other than that I have to write and bracket and so forth. So n times log 2 times pi. R knows what pi is. Then minus 0.5 times n times log sigma 2 minus, so minus into bracket. And this one I need a fraction, so it's okay to do this. So 1 over 2, so 2 times pi, 2 times sigma sigma 2. Okay, 2 times sigma 2. Then we multiply it by the sum of x minus mu, right? And then all squared. So that's it for our log likelihood function. And next is return. So what do we return? We return negative log like. Okay. So now we are in a position to draw our function. Remember I said you should put it in that. Okay. So now if we run this, return did not work. Okay, so the return is actually outside the bracket. Okay, so you see how you can make mistakes. Okay, so the return should be within the function. So let me do it again. Okay, so now it worked. Now I trust everything is okay now. So now what we want to do is that we optimize it. Optimize the function. So how do we optimize the function? We can go and copy what is up here. Yeah, so up here and come and take in what we need to do, or what we will need. Okay, so optimize the function. So fit norm, fit n. Okay, so here the parameters we need 2. So this should be a vector, right? Now the function that we are trying to optimize is not that one, but rather what? Norm this. Okay. Method, maybe we can use LFG. If we use LFG, then we need the lower bound. What is the lower bound? Remember, the first one is the mean. So the mean, it has to be, let's see, negative inf, but the variance is 0. Okay. Then the upper bound, we can also say they are both infinite, right? Infinite. Patient through data. What was our data for the normal? We haven't. Okay. It's air quality, right? Air quality. When. But now it's not data, it's y, because look at my function. My function over here has parts and y, not data, so you have to be careful. Other than that, I can make that mistake for us to check, because I know we will not get it. But it's good for us to learn from it. So let's see. So you see, when we come here, it tells us that unused argument, data is equal to, so the function cannot find any data anywhere. Meanwhile, it was y, so we have to put in y like this, and then we do. Okay. Object x not found. So it means we were calling for x somewhere, but x cannot be found. I think it's my mistake, because here I use x, but instead I pass in y. Okay, so here it should be y, right? So once I correct this, I have to go back. Remember, I had learned y, but here I said sum of x. So I have to go back. Once I've changed anything, I have to rewrite this. Okay. So what have we learned over here? That we can actually debug our codes to get the results. So now I get my results. Okay. It works perfectly now. Okay, so now I click over here, and there it is. So the parameters are what? 9.995 and or 12.33, the um, value of the function is positive. Remember, if you notice this, the log likelihood for the discrete case was negative. It was negative all the time, and then that of the continuous case, continuous distributions are positive. So we can find our cake information, AIC, and see what AIC fit in. Okay, so in this case, our own, we have to use our AIC that we did, because we wrote our own function. So the AIC, where is my AIC function? If I want to use that one, because I wrote something. Yeah, there it is. So, okay. So if I want to get to know the AIC, I'll call. Oh, it's not good because it's now going to conflict with the inbuilt AIC. I can't have a function that has the same name as an inbuilt function. So if I want to use this function, I have to go back and say AIC maybe own, something like that. Okay, dot own, and then this one I can do so like that. Then when I come here, I say AIC dot own. AIC dot own, then number of parameters k is equal to 2 because I know already, and log likelihood will be fit in, and then the value. Okay, so there I get negative. Okay, so usually the cake information for continuous cases are negative. What do we need? Okay, so here when we are comparing, we are interested in the one with the minimum AIC. Okay, if we have two models and I fit them with some estimation methods, and the AIC of this is smaller than the other, we term the smaller one the better of the two. Okay, so that's it, how we do our estimation, and then how we can also check for the fit of our model. Okay. So that brings us to the end of our discussion on maximum likelihood estimation. Okay. So the next thing I'll discuss is how we can obtain standard errors. Okay. Now the other ones, you see, when I use fit.days and fit, I can get a standard error straight away. When I write my own function and then I use the optim to optimize it, I cannot get the standard error right away. But however, I can obtain what? The Hessian matrix. If I have the Hessian matrix, then it is possible for me to find the standard errors, because the inverse of the Hessian matrix will give me the covariances and the variances, okay, of my estimator, and then I can find the standard error of it, right, between the estimates. Okay, so what do I do? So the it's okay, so it's obtaining standard errors. Standard errors are also good for us because it gives us an indication of the mean square error associated with that estimator. Okay, so as I said, in our case, we use optim. So that optim, the optim function, remember that we can set Haitian, we can get our Haitian. If you go in the Haitian, if you set Haitian to be true, so by default it is false, but if you set it to be true, you get a Haitian matrix. So if you look at our function over here, this is a Haitian matrix because we have two parameters, okay, mean and sigma squared. Okay. Now, if we go to the where we were doing this one, okay. Now here, our Haitian matrix is just 1, so it's just so that one is easy. You find the inverse, you find the square root of it, you get your standard error. Okay. So that's it, because there's just one parameter, so it's easy. So the Haitian matrix is just a constant. Okay. Now, so if you want to get a standard errors, then it means you need to put Haitian to be equal to true, just like I have done over here. Remember, T is true, or I can write it in full as true, whichever way it works. Okay. Okay. Now since we have to perform operations on the Haitian, it is also important that we store the results from the estimation into an object. Okay. So once I have my Haitian matrix, all I need to do is to store it. Then I take it up, and then I'll use it now to find my standard error. So that's the next thing we will do now. Okay. So I'm going to take the normal one to go through the process, and I'm sure once I have done that, you should be in a position to do it anytime you are faced with computing the standard error. Okay. So here, I would say inverse of Hess will be that. How do you find inverse in R? We use the function solve. So if we want to find inverse, we use solve. Okay. So if I say solve, okay, so it's matrix. So when you have a matrix and you want to solve for, so we can use it for solving for systems of equations. So if you have simultaneous equation of 3 or more variables and so forth, you can actually use solve to solve for it, because it's solved for the inverse of the function. So what I'm going to do is that I will solve for the inverse of the Haitian matrix. So I call my estimate fit.n, okay, and then my Haitian matrix. Okay, so when I do this, I have the inverse of my Haitian matrix. Okay, then I can have it like this. Okay, so that's the inverse. Now, the diagonals are the variances. Okay, so when I take the square, the diagonals are the variances. So if I want the diagonal, if I use die, the function die, right, on this, I get my diagonal values. You see the diagonal values. Okay, so what I'm going to do is that, because they are variances, I'm now going to find square root of it, and then I get my standard error. So my SC of the estimators, I should say estimators, are the square root. So square root is SQRT, and then I have this. Okay, so there I have, so my standard error is what? Is this. So the standard error, so what it means is that if I want to put this, I can put this in a data frame, okay, and then I have a data frame. So after my estimation, I have my parameters. So I will say estimate are the fit n and then you have par, okay, and then my next level is a standard error. Standard error. Standard error. So that I have to, because I want to put it as one word or as a string, I must put it in curly bracket, and then now I take my SC. Okay. So if I do this and I say, so you have estimate and standard error. If I want to name the rows, I can do so that it becomes easy for anybody to see this. So it's just row names. So row names. Then I have what? The first one is what? Is the mean, right? Because that's the mean. Or the mean, estimate of the mean. And the other one is what? The variance. Variance. So the variance and the mean. Okay. So if I do so, now if I get my tab, I have what? My estimate, which is this, my mean. If I want to round it, I can round it to 2 decimal places or what have you, and so forth. So that's how we compute standard errors. If we go through our method to get what is it, our maximum likelihood estimate, and then we want to find the standard error. So we can compare the standard errors of each of the approaches that we've used, and in that case, because they are all estimating the same thing, okay, we will choose the one that gives us the minimum standard error. So that's it, and that should be enough for this session.